Nice, student. Previously, we system. We talk about solid liquid system. Mostly, we talk about the solid liquid system dissolve in liquid. So you dissolve in liquid. We will talk about the solubility. Solubility of a solid liquid is maximum amount of that maximum amount of solid that can be dissolved in a specified amount of liquid. That means at the constant temperature or pressure, what is the maximum amount of solid that can dissolve in liquid, which constitutes the saturation or solubility. And also these properties vary from one solvent to another. So we call it a solution. Solution this includes solute with its solid and solvent liquid. Solute is solid form like sugar syrup. That's why sugar dissolved in liquid. It syrup at any temperature or pressure. That's we call this solubility is the maximum amount of sugar that can dissolve in liquid or in water at constant temperature. We call this solution is the saturated solution. Okay, if a saturated solution is cool, the solubility of the solute decrease in order for the cool solution to equilibrium. Okay, some solute must come out that with the solid crystal. If the example of this uh, for this saturation state, and the solution said that it solution that the concentration is higher than saturated supersat solution. For example, if we talk this is the solubility of calcium nitrate, calcium nitrate vary with temperature. If temperature increase, the solubility increase. If we start at this point, 100 degrees Celsius, if you cool the temperature, this one is the undersaturated. If you stay at 100 degrees Celsius, then 100 degrees Celsius, if you add some calcium nitrate, the solution can dissolve, so it's faster until it reaches this point. Until it is point, these are the maximum of calcium nitrate that can dissolve in 100 gram. I suppose at this point is approximately 240 gram of calcium nitrate per 100 gram of water. It is the solubility of calcium nitrate at 100 degrees. Also, if we prepare the concentration as only about 170 gram per 100 gram water at 100 degrees Celsius, then you cool the temperature. At this point, it's undersaturated, not saturated. If you cool the temperature until this temperature, that's right, about 80 degrees Celsius. This point, the concentration at 170 is undersat at 100 degrees Celsius, but it equilibrium or saturated at 80 degrees Celsius. For this point, is the solubility of calcium nitrate at 80 degrees Celsius. Also, if you decrease or cooling further, get concentration here in this zone. This zone we call it supersaturated because it's greater than or higher than solubility. This side is solubility. Okay, from 100 cooling to the 80. For the 80 is saturated. And then you cooling further, you get like the supersaturated. At this point, for example, you cool to this point at about 65 degrees Celsius. For this point, you get it the supersaturated. And for this point, some crystal or some solute potassium nitrate and crystal out like from liquid to solid form. Amount of is the supersaturation sign. In this case, is about 170 is about 50 gram of Germinated will crystal out with 100 gram of water. If you cooling further, right, the supersaturation will be larger, right, at about 40 degrees Celsius. If you could further write it to about 0 degrees Celsius, the saturation is larger. It depends on the temperature. Supersaturation degree is the difference between the actual concentration and concentration at equilibrium. Let's get it show you why it can crystal out. For this system, under sat or saturation, the system only one phase, two components. Right? One phase is liquid, two components is solvent and solute. If the concentration and the cooling is until this point or until the zone of supersaturation, this is a supersaturation zone, is solubility, and the zone that below the solubility we call it saturated, undersaturated. The zone at above saturated, the crystal can turn out some liquid solid system. That is a liquid solid system. And the line, that's the solubility line, and below that is called the liquid system. Okay. For this, we will give you an example of the crystallization and filtration. We have 150 kilogram saturated solution of silver nitrate at 100 degrees Celsius. We start at 100 degrees Celsius. And we have 150 kilogram of solution. This case, the liquid. This liquid, we have silver nitrate dissolved in water at 100 degrees. And then we cool to 20 degrees Celsius by catheterizer. We send this solution to the catheterizer which cooled from 100 to 20 degrees Celsius. And we have no the silver nitrate. And they be forming a silver nitrate crystal. So you cool from 100 to 20, there are some silver nitrate crystal and some saturated solution. The crystal filter from the remaining solution, and then you send the crystal and solution to filter. And then after filter, we get two product in the filtrate. That filtrate contain solute and solvent. Solute and solvent saturated. The filter cake, and also this is filtered. This is the filter cake. And the filter cake will contain 80% solid. For this contain 80% solid silver nitrate in the solid form and 20% in liquid form. 70% in liquid form at a saturated solution we refer to the solubility, or we refer to the solubility line, but for this it is not solubility line. And then the filtrate pass to dryer. With dryer, the water will evaporate out of this. Then we have two products, the vapor of water and solid silver nitrate. Calculate the fraction of silver nitrate in the feed stream. How much silver nitrate in the feed stream? And recovery dry crystal, how much the dry crystal? And amount of water that must be removed from dry. Calculate amount of water evaporate, amount of crystal recovery, amount of solute in the feed. For this case, we base it based on 150 kilogram of feed. For this case, we can draw the flow chart by the first step. We send the feed to the catheterizer. Feed is 100 degrees Celsius. It's 150. The feed is saturated solution. The saturated solution would mean the feed at solubility. For this case, you can know the composition of the feed by you read the solubility data. Okay, and then you send to catheterizer. get the product is silver nitrate crystal and saturated. The saturation is equilibrium also, but equilibrium at 20 degrees Celsius. 20 degrees Celsius. And also you send this product to the filter. The product of filter will have to the filtrate. Filtrate is only liquid, and filter cake is liquid and solid. The filter cake also in saturated solution. This include solute and solvent at equilibrium or solubility data. For the filter cake, have two components. We have the crystal and solution. The solution also in equilibrium or solubility at 20 degrees Celsius. And then you send filter cake to dryer. Dryer we have two products. First product is evaporation. Water evaporate out from the vapor form of water. And the product another is solid crystal. Okay. For this case, we denote the unknown, right, as M1. M1 is mass of solution in the filtrate. M2 is crystal of silver nitrate in the filter cake. M3 is the solution in filter cake. Please note that solution is contain silver nitrate and water in liquid form. M4 is the vapor water that evaporates out, and M5 is the silver nitrate in crystal. Okay. The first step, you have to determine what is the solubility of silver nitrate in water at 100 degrees Celsius and 20 degrees Celsius. You know that we have no this data. In this case, we open the early handbook. With the data shown in this. Okay. For the solubility data at 100 degrees Celsius to fit the electrolyzer, we want to fit saturation. That means the solubility. It is liquid form, silver nitrate and water. How much silver nitrate, how much water you calculate on the solubility at 100 degrees Celsius. And from the Pearly handbook, you know that 100 degrees Celsius, we have 952 grams silver nitrate in 100 gram water. That means total is 1052 gram of total. Then you can calculate fraction of solute. The solute is 952 divided by 100 plus 952. You get the fraction of silver nitrate is 0.905 gram silver nitrate per gram total. And then you can calculate the fraction of water by 1 minus this term, you get 0.095 gram. This is the fraction of the feed. Right? This contains solute of silver nitrate in liquid form, 0.905, 90, and water is 0.095 or 9.5. This is composition in the feed. In the feed, you know amount, you know composition. Next one, the product out of the electrolyzer. This includes silver nitrate crystal, saturated solution, 20 degrees Celsius. Filter also at the same temperature. Okay. For the filter cake, the solution is in equilibrium at 20 degrees Celsius. At equilibrium means the solubility at 20. Okay, for the next step, you can composition of electrolyzer. Composition in filter cake, composition in filtrate, 20 degrees Celsius. The chemical engineering handbook, 20 degrees Celsius. You know the amount of silver nitrate is 422 grams silver nitrate dissolved in 100 grams. And then you can calculate the same way like this. You can get the fraction of silver nitrate in water is 69% and 31.1% of. And then you can know the composition of solution out of the electrolyzer. Also composition of solution in the filtrate is 0.9% and 31.1% water. Also the solution in filter cake is the same composition. For this, you know the composition feed to the electrolyzer, feed to the filter, in the filter cake. For this, unknown is M1, M2, M3, M4, M5. We have 4 unknown. If you balance overall, have 3 unknown but only 2 balance. Okay? You have to take the degree of freedom. If you calculate the composition of the filter cake, composition of the filter cake, what is the composition of the filter cake? Cake is M2, that's right. M2 means the composition of silver-nated crystal of liquid amount is 80%. 80% is solid. In this case, it's M2 plus M2 plus MT. M2 plus MT is the amount of filter. M2 plus MT is the amount of filter. But filter cake includes 80% solid. That means M2 equal to 0.8 M2 plus MT. M2 plus MT is the total amount. M2 is only solid. Solid crystal is 80% of filter. For this case, you get M2 equal to 4 multiplied MT. And then you try to balance. For this case, you can balance. If overall, you cannot solve. Like overall, we have M1, M4, M5, 3. You cannot solve. We have 3 unknown, but only 2 components, water and silver nitrate. But 2 degree of freedom, 3 degree of freedom. That's not 2, 1 degree of freedom. For that case, you can, the next step you about the categorizer and filter. If you balance categorizer and filter, categorizer and filter, we have M1, M2, M3. Right. We have 3 unknown also, but we have 2 independent balance. We have 2 independent balance. But also, you know, right, the M3 and M4, you can correlate it. You have the 80% of solid in filter cake. In this case, we have 3 unknown, minus 2 balance, right? And minus 1 information, you get 0 degree of freedom. For this case, you can solve like the balance around categorizer and filter. Because you know 3 unknown but 2 independent balance, 1 information. You can solve for that. But for overall, you cannot. We have 3 unknown, only 2 balance, and you get. Let's get the first step. You have to balance on categorizer and filter. Okay. First step, you balance water on the categorizer and filter. In this case, there is no generation, no consumption, and no generation. Okay, input equal input water. Input water is 0.095 multiplied by 100. This is input water. Input water. Or output water. The output water in 2 forms, right? Water in filtrate and water in filter. Water in filtrate is 0.311 multiplied M1. 311 multiplied plus 311 multiplied M3. 311 multiplied M3. Also, next you balance with the total mass balance. That's right. The total mass balance around the mass balance is 150 feet. We have output M1, M2 plus M3. It is 150 equal to M1 plus M2 plus. Okay, you have M1, M2, and 3 unknown. But also, you know M2 equal to 4, M3. You can solve for that. 1, 2, 3 equation. You can solve for that. You can solve M1 equal to 20, M2 equal to 104, M3 equal to 26. And then you balance next is the silver nitrate balance or the overall silver nitrate balance. You balance overall silver nitrate balance. That's why we have 150 multiplied 0.905 of feed silver nitrate. How about the output silver nitrate? The output silver nitrate, that's like we have 3 output filtrate, water and silver nitrate, but we have 2 output of nitrate, silver nitrate, that's 0.689 M1. You know M1 already from it, and then you can solve for M. You know M5, you know M1, M2, M3, and also if you would like to calculate M4, you can balance overall mass balance. 150 equal to M1 plus M4. This case, we balance overall process. It is 150. M1 plus M4 plus M5. You know M1, you know M5 already. You can calculate the amount of liquid of water evaporated for each kilogram water removed in the dry. Also, you can calculate the percent recovery. Percent recovery is the silver-nitrate crystal out divided by silver-nitrate feed. Silver-nitrate crystal out is M5. M5 is the silver-nitrate crystal out. How much silver-nitrate in the feed? Silver-nitrate in the feed is 0.905 multiplied. You can calculate the recovery percent you multiply by 100. Is the silver-nitrate recovery out system. Silver-nitrate in the feed by 100%, you get 9.9%. And for the next example, right? For this case, we have an aqueous potassium nitrate solution contain 60% weight potassium nitrate percent 80 degrees Celsius feed to the crystallizer with cooling crystallizer. In this case, we cooling from 80 degrees Celsius to 40 degrees Celsius and determine the temperature at which the solution reaches saturation and percentage of potassium nitrate. For this case, first we have to calculate what the constant or the temperature at what is the temperature at the saturation equilibrium. For this case, we cooling from 80 to 40 to 40. For that case, during your cooling 40, we get the crystal, but before 40, what is the saturation of this? Saturation of this. First step, you have to convert feed concentration, that's like from solute solvent ratio used by the equilibrium line. That's the case. Okay, for this case, we feed 60% of potassium nitrate. That means 60% is based on 100 kilogram or 100 gram. That means 60 gram of potassium nitrate divided by 40 gram of water. In this case, we have two components, water and potassium nitrate. Potassium nitrate 60, that means water is 40. Okay, for this case, you calculate the ratio of potassium nitrate and water, you get 1.5 gram potassium nitrate per gram water, or equal to 150 gram potassium nitrate per 150 gram per 1 gram. And then you can check with the equilibrium line for that case. In this case, we feed at 150 gram of silver nitrate per 100 gram of water. What is the saturation of this concentration? You can drag the horizontal line to cause the solubility line of silver nitrate. And then you drag the vertical line to the temperature. For this case, the saturation for this concentration is about 24. For this, the first answer, we get it 24 degrees Celsius. That's it mean. For this case, we start at 80 degrees Celsius. 80 degrees Celsius with 150 gram of silver nitrate per 100 gram of water. And then you cool to 40. At this point, This point is supersat, but its 80 is undersat. Undersat is 74. It is confirmed that we will get the crystallization crystal opposite at 40 degrees Celsius. That's right. Because we cool from HD, the saturation is at 24, and then for this system we cool to 40. At 40 it's supersaturated. The driving force can crystallize. This confirms the crystallization. For this case, the basis we use like 100 grams of feed because we know the feed concentration. 50% calcium nitrate, 40% water. It at 100 kilograms is at the basic calculation. And then after crystallizer, we have the two net like the saturated solution at 40 degrees Celsius and also crystal. M1 means the mass of saturated solution, and M2 is the mass of crystal. This solution in equilibrium, and also X is the fraction of potassium nitrate. If you know X, you can calculate the fraction of. So for this case, we have three unknown. Three unknown. You have two composition. And also you have to calculate the solubility at 40. You know the output is saturation at 40, and then you can calculate the solubility at 40, and then you know at 40 you can evaluate the X. For this case, we have three unknown, but two balance and one information. The information is saturation at 40 degrees Celsius, low degree of freedom. Please remember that we have M1 and M2 is unknown. M1, M2, X is unknown. We have balance on silver nitrate, on water, or total mass balance, but we have only two independent. 3 minus 2 and minus 1 information. The information is solubility at 40 degrees Celsius. And also you can evaluate solubility at 40 degrees Celsius. It's approximately 60 kilogram silver nitrate per 100 kilogram solution. This case is gram per 100 gram or equal to kilogram per 100. It's the same ratio. The solubility is 60 kilogram silver nitrate per potassium nitrate per 100 gram water. Then you can calculate fraction. In this case, the total mass is 163. That's 163. Potassium nitrate is 63. You get 0.386 kilogram potassium nitrate. 38.6%. Okay, you know X, and then you can calculate the fraction of water. And now you know X, you have only two, M1 and M2 unknown, and you have two balance. Okay, solve for that. In the first step, we solve water balance. Water balance, that's right. Water input is 0.4 multiplied 100 equal to 1 minus X M1. That's right. 1 minus X in the fraction of water. M1 is the total mass. Go to M1 multiply 1 minus X is 0.386. You can solve M1. And then you can make the total mass balance. The total mass feed is 100. Output is M1 plus M2. Then you can solve for M2. M1 already. The next step, you calculate the percent of potassium nitrate. Potassium nitrate in the feed. What is the potassium nitrate in the feed? Potassium nitrate in the feed is 60 kilogram. You call it 60%. 0.6 How about the Germinated crystal? Yes, 33.9. Did you get the percent recovery is 58. This is the example of solid liquid equilibrium. More at equilibrium or at the saturation system, we call that solubility. For the example, we start at ST. We conclude for that. We start at ST and 150 kilogram per 100 kilogram. At 150, ST is undersaturated. If you cool to 24, this is the saturation. If for this system we cool down to the 40, this is the supersaturation that we realize. This is how. However, in the solution of solid in liquid system, let's talk about some anhydrous crystal or hydrated crystal. In this case, the anhydrous crystal water free. After you crystallize, there is no water in the structure of we call it the anhydrous. For another system, we call it hydrated crystal. After you crystallize, there are some crystal in the structure of the bond to the crystal. We call it is the hydrate. For example, magnesium sulfate. That's right. This is no water or anhydrous magnesium sulfate. Percent weight is 100%. That's concentration is greater than 100 degrees Celsius. After you crystallize at greater than 100 degrees Celsius, you get anhydrous magnesium sulfate. If you crystallize at about 67 to 100, you will get the magnesium sulfate monohydrate. It's one molecule of water like this. And also, magnesium sulfate hexahydrate is 6 molecules of water. And at another temperature like this, at the very low temperature, you will get the magnesium sulfate with the hydrate is about 12 molecules of water. Example, right? For this case, some system after you crystallize solute out of the solvent, there are some solvent bound in the crystal. We call this the hydrate crystal, especially for water, we call hydrate. If the solvent is not water, we call it solvent. Or the solvent is water, we call hydrate. Hydrate or hydro is mean water. For this example, right? Talk about an aqueous solution of magnesium sulfate at 104 degrees Celsius. Is containing 30.1% weight magnesium sulfate is fed to the cooling crystallizer. It operates at 10 degrees Celsius. That means we cool from 104 to 10 degrees Celsius. And the steam leaving the crystallizer is slowly of solid magnesium sulfate. Hepta means 7 molecules of water. After you crystallization, we have the solid in the form of magnesium sulfate, hepta, hydrate. Let's get. Okay, the next do you use to read data from Perry Chemical Engineering Handbook and show that a saturated solution at 10 degrees Celsius contain 23.2 weight% magnesium sulfate. Okay, the output is 23.2 magnesium sulfate. Mean unit should be ton. For this case, we use at the ton. But the answer is the question is determine the rate at which the solution must be fed to the crystallizer to produce 1 metric ton. 1 metric ton or 1 ton equal to 1,000 kilogram heptahydrate per hour. For this case, we have to calculate M1, like the total mole, total ton per hour of feed. Okay, for this case, we base it at the 1 ton magnesium sulfate per hour. 1 ton magnesium sulfate heptahydrate is the product. It's the basis. Okay. Next, you draw the flow chart. Flow chart M1 is the feed, and you don't know the feed. That's one. And the output, we know the 1 ton magnesium sulfate heptahydrate, but the total mass you don't know. Okay, we M1 is total mass in, M2 is total mass output, mass net in mass. The feed composition you know already. The feed composition is 30.1% that's of magnesium sulfate. Then you know 0.699 on 69.9 ton water per ton. action of water. How about the output? The output you have to calculate based on the solubility of magnesium sulfate, which show already from the chemical engineering handbook with the solubility is 22.2 weight percent magnesium sulfate. No, right? Fraction of magnesium sulfate is 0.232 and another one is 0.768 is water. Okay. Composition of input, composition of output. And then we have two unknown you can solve directly. In this case, input equal to output. There is no generation, no consumption. First step, you make the total mass balance. Total mass balance input is n.1, this is the mass rate. Output, we have 1 ton magnesium hydrate per hour plus M2. M2 is the solution. Or the output, we have and solution is M2. The next will balance is magnesium sulfate balance. About magnesium sulfate, the input is 0.301 M1 is speed magnesium sulfate balance. So to 1 ton magnesium sulfate. This the input is magnesium sulfate, but output in terms of magnesium sulfate heptahydrate 1 ton. You know the molecular weight of magnesium sulfate. This the magnesium sulfate with 7 molecules of water, the molecular weight is more than 46. But for this case, includes 120.4 tons of magnesium sulfate. Calculate based on the molecular weight relation. As the magnesium sulfate in solution. In solution include 0.232 ton magnesium sulfate per ton multiplied by M2. Then you can solve for M1 and M2. We have two equations. M1 equal to 3.71 ton per hour. M1 means the feed solution. M2 means of the output of. I will stop for break for this before I will continue after next.